start recording so all those people who didn't show up for class still get the knowledge they need to make a good impression on the exams. So anyway, don't forget your activity. Your activity is not going to be done in class. You have to submit it by, do it yourself and upload it to Canvas by, I believe it was midnight on Wednesday for your class. And so go ahead, don't forget that. It's really going to help you kind of help study for the exam. So, okay. And then our exam on the following Monday is going to be focused on these last few chapters, chapters 8 through 11, but it will, chemistry is cumulative, so there might be some questions that seem a little more basic from previous chapters, and that might be true. And then we have our final, which is, of course, covers all 12 chapters. Should the activity just include all of the mechanisms from chapter 8? It can, but it's like hydrohalogenation. How does it, what is the regio consequences of hydrohalogenation? You're going to say, oh, well, Markovnikov's addition. Okay, what does that mean? Okay. And then knowing that it goes through, whether or not it goes through a carbocation or not, that's important, because in the first step of our addition of HBr across a double bond, it's the hydrogen adds across the double bond, giving us a carbocation, and then the bromine comes in last. So that tells us exactly where the bromine is going to be. And as we'll learn in the radical mechanisms, that's not the same. It's actually backwards of that, because the bromine attacks first and it ends up giving us our least substituted bromination thing. Okay, so let's see. Will the final resemble the tests we've taken through the semester? Yes. Same style of question. They're just different questions covering all the same kind of topics we saw before. Will this follow the same format? Yes, it'll follow the same one. It's going to be a little longer. Let me see. I think there's 60 questions on it because we have 2.5 hours. So it's going to be longer than any test you've had, but it's because it also has to cover all of the chapters. Okay. Is there a drop exam or final replacement? Not unless you have something signed from the Dean of Students saying you were absent for the day of the exam. So, and then there are things we can do there, but there are no drops on that. But again, I do curve each and every exam, and the class average right now is looking pretty good. Turn in that activity because it's, 95% of it is participation. So turning in the activity, and looking at that, number one, it's going to help you study. Number two, it's a participation grade. So I should be getting the final numbers back from SI here in next week. And so that will start to populate in Canvas as well. Okay. All right. So let's move back onto our chapter on radicals. We have about 5 or 6 more slides left in radicals, and then we're going to hit alcohols and ethers in today and on Wednesday. Okay. So we learned that selectivity comes from having a lower reactivity, and having that lower reactivity allows you to wait around for the more stable radical to form. And when we do this, we get selectivity of our bromination, specifically on the tertiary site, our tertiary hydrogen versus our primary hydrogen. And we found out that they had selectivity ratios, so we could predict the product ratios based on that. Okay, so don't forget, radicals have an initiation step, a propagation step, and the termination step. The stability of that intermediate and the propagation step is what gives us our selectivity. Okay, so what about regiochemistry? Well, just like with carbocations, when you have a radical, you have a p orbital above and below the plane. And so you're going to get a 50-50 mixture of the R or the S, depending on how you do it, because it's like a carbocation, it's going to give you that racemic mixture, because carbocation is just that same unhybridized p orbital, but it was empty. A radical is an unhybridized p orbital, but it has 1 electron in it. So that's why the stereochemistry is racemic on that one. The other thing that's interesting about radicals is they do not rearrange, and we can use that to our advantage, okay? So in the case of, we had 2 substrates here. First of all, we like using radical situations, radical reactions, especially when you have really unreactive bonds, like The carbon-hydrogen bond is very unreacted to most other things. Most of the time you just burn it, right? But the radical abstraction of a hydrogen from a hydrocarbon means that you can do chemistry and make it functionalized to do other chemistries. But the radicals will not rearrange like carbocations. So if you want to be very site selective with your system, using a radical system can generate sometimes a cleaner reaction without those rearrangement products. So in the case of trying to get this substrate here, if we tried to get that substrate by the substitution of OH under acidic conditions, what we're going to do is we're actually going to pop that OH off by protonating it and giving us a carbocation. That carbocation is then going to rearrange from a secondary carbocation to a tertiary carbocation, and our bromine is going to end up on a tertiary carbon. Okay, that's not the product we're looking for. The product we're looking for is the secondary alkyl halide, so we can do some other chemistry to it. We can do some other substitution reaction. Okay, we can't get to that using the carbocation, but because the radicals do not rearrange, we do get the product that we're looking for, that secondary alkyl bromide. Okay, so that's with double bonds and that's with single bonds. Okay, what about benzylic bonds? Okay, so first of all, let's remember what benzylic means. Is when you have a benzene ring and you have any hydrogens that are one carbon off the benzene ring, those are called the benzylic hydrogens. Okay, now it's very difficult to brominate the benzene ring with bromine itself or a bromine radical because you would distort aromaticity. And as we'll learn next semester, you actually have to use a catalyst to change the reaction mechanism. Okay, so we're not going to react the benzene ring. However, if there are sp2, sp3 hybridized hydrogen bonds on that position just off the benzene ring, that is going to be 100% substituted by bromine. Now, remember, we talked about the benzylic radical being very stable and very reactive because it can be spread around the ring temporarily, and we can switch that out to give us bromines very selectively. Okay. However, it only works with bromine because of its selectivity. Slightly slower reaction, it forms a more stable product. The chlorination is not selective enough and gives us dichlorination, trichlorination, etc. Okay, so we can take that advantage of the reactivity of that the benzylic position and use bromination there. Okay. Now, with allylic, bromination is also very easy as well. Remember that our allylic radical is also stable, if we form a radical right here, in conjugation with a double bond, because we can share that radical across those two carbons. Then we see that it can, it's number one, more reactive than a regular radical. And so we actually can get very highly selective bromination at that site because of the selectivity of bromine and the stability of that allylic radical. Okay. However, it does have a side reaction. So instead of having the bromine radical abstract a hydrogen radical from the allylic position, creating that allylic radical, what can happen is that bromine radical can add across the double bond. And if that bromine adds across the double bond, then you have an opportunity for that radical to abstract bromine radical from bromine just floating by and end up with a dibromo product. Okay, which is not the desired product. Your desired product is the one where you take this hydrogen off using a bromine radical, generating a radical in that allylic position. So this is a side reaction. And once you get those two bromines on there, you're always going to have a little bit, you know, by controlling conditions, you should be able to minimize the amount of dibromine. Now, one of the ways to minimize this a side reaction is make sure your concentration of bromine is very low in solution. Okay. That way, even if you do get this radical here, it doesn't abstract it from bromine. It actually does the reversible reaction and gets you back to your original product. So The other advantage of the allylic bromination is the fact that we do not form that addition to form that bromonium cation, okay? And so because we don't form that, we don't actually get addition across that double bond. We have that allylic abstraction of the hydrogen radical. Now this is really helped by using a non-polar solvent. Remember, if we're forming that bromonium cation, it has to be supported by the solvent. And so by using a non-polar solvent, we can minimize the amount of that bromonium ion formed and maximize the amount of having the allylic hydrogen being abstracted by the bromine radical. Okay, another way to enhance having the bromine radical react selectively is to actually not use bromine at all, okay? What we use is we use a compound called N-bromosuccinimide, meaning that there's a bromine on the nitrogen. So we have a weak nitrogen-bromine bond, okay? When we have that weak nitrogen-bromine bond, we can hit it with light, HNu, in a solvent that cannot be halogenated because carbon tetrachloride is one of those solvents that already has halogens on it, so it doesn't react in a radical situation. And we can have just that bromine radical around, reach out, abstract a hydrogen, have that little bit of bromine in the solution, react with our allylic radical, and then generate our allylic bromide right here. Now, the key here is to have a very low concentration of this HBr because we can actually have that HBr react with NBS, okay? And so we have to be careful about what solvents we want to use. We want to try to use as non-polar a solvent as possible so it doesn't support the hydrogen bromide, but we need to use a little polar enough solvent such that it dissolves the NBS. Okay. So here's where we're starting to get very selective, not only about the reagent we use to enhance the yield of our allylic bromination here, but also the solvent we use when we try to do these. And I remember there's a couple mechanisms we had that solvent was very important. Remember, don't forget. All right, so we can all, when we see it done, we looked at HBr adding across a double bond without a radical. It would add Markovnikovs, meaning the hydrogen would go to the more substituted side. The hydrogen would go to the more side with more hydrogens. The bromine would go to the more substituted side. That doesn't happen when we use a radical mechanism. And it's all because we're looking to form that most stable radical. In the case of carbocations, the more substituted center is the more stable center for carbocations. The same is true for radicals. The more substituted the center is, the more stable it is. And that's, remember from earlier in the talk, due to hyperconjugation, which means that we're going to get our bromine on our less substituted side. But all the steps in the system are the same. We're going to do one, we're going to initiate. So we're going to use, in this case, a peroxide. Right here, our oxygen-oxygen bond is very weak. It breaks, forming two radicals. It abstracts a hydrogen from the HBr, giving us our bromine radical that then attacks the double bond. Now remember, in the propagation step, every time you have a radical attack a neutral species, you still get another radical. And then that keeps going and going and going until the termination step. The termination step can be either the abstraction of hydrogen from HBr to generate your final product, or you can also have the radicals on two carbons joined together, which is a side product of our reaction. We can have two bromines react to form each other, and then that could actually give rise to another side product. So the best, most propagating step in the system is when we generate our desired product with bromine. Okay. Now, it's interesting that it works really well with HBr, but it doesn't work with HCl, which is less acidic, and HI, which is more acidic. And it all comes down to the bond energy of the hydrogen-chlorine bond or the stability of that iodine radical. In the case of using HCl in the system, the HCl bond is stronger than having it be abstracted from by the radical to give us our final product. Therefore, the reaction is actually endothermic and does not proceed. Okay. In the case of iodine, iodine is actually more stable as the radical than in its form, and therefore it's also an endothermic reaction and therefore does not proceed. So it's unique to HBr adding across our system. So when you see alkene HBr peroxide, you should know exactly what's going to happen. Now let's compare the energy diagrams to the two different radicals formed and prove to ourselves why it adds the opposite of the carbocation mechanism. It adds anti-Markovnikovs. Okay. So in the case of our first radical coming in and interacting with our double bond, that first bond forming is one electron from the double bond and leaving the other electron behind. So by leaving the other electron behind on the more substituted carbon and generating a new sigma bond with those two other radicals of with those two other electrons, we generate a lower energy diagram, a lower energy transition state to yield our more substituted alkene. So that's our lower line on our coordinate diagram. Now, if we were to go ahead and make that sigma bond and have that radical stay on that least substituted side right here, this would be a higher transition state, and therefore that is not going to add that way. That's the way it would add if we were going to add HBr without peroxides. Now let's compare and contrast those two mechanisms. It all comes down to stability of our intermediate, okay? So in the case of the radical, the more substituted radical is more stable, but the bromine attacks first, meaning the bromine is going to be on the least substituted carbon. In the case of HBr, the hydrogen is added to the double bond first. Therefore, we have to generate the most stable carbocation, which is the more substituted. Bromine comes in second, and that's why it's on the more substituted carbon, okay? So that's a very good compare and contrast. If you want your bromine on the least substituted carbon of the alkene, you use peroxides. If you want bromine on the more substituted carbon of the alkene, you don't want to use peroxides. You want to use that polar protic solvent, make your carbocation, and then have your Markovnikov's product. Questions on the anti-Markovnikov versus Markovnikov mechanisms? Okay, well, that is radicals in a nutshell. I'm going to go ahead and pull up our alcohols. So we have two modules in chapter 11. It's going to be alcohols and then a little chapter on ethers. I'm going to talk about the most important aspects of ether reactions, probably in the alcohols chapter, but there are a couple little reactions that you should know about ethers as well. So the first thing we need to think about alcohols is, number one, they are amphoteric. Okay, amphoteric, meaning they can act as a base or they can act as an acid. Okay, think about it. It's protic and it has two lone pairs. The proton on it wants to act like an acid. The two lone pairs want to act as a base. Okay, but it's a weak acid and a weak base as the alcohol. What does that mean? Well, that means when we protonate it, it becomes a strong acid. Okay, so the protonated form of methanol is a strong acid, pKa below 0. Okay, and when we take that proton away, they become very strong bases. Okay, so alcohols have that really cool, unique property about being protic, being able to absorb, being able to adhere to a hydrogen, or being able to give it up and do either strong acid work or strong base work. Okay, so we're going to instead look a bunch of different reactions on how to make them and how that we can interconvert between carbonyl compounds and other things. The first thing we're going to do is we're going to do some SN2 reactions. I don't know why it says SN1. We're going to do some nucleophilic substitution reactions. to form alcohols. Actually, they're addition reactions, nucleophilic addition reactions. It's not a substitution reaction, it's an addition reaction with a new reagent, some organometallic reagents, and the acetylide ion. We're going to do reductions, we're going to do oxidations, and then the ring opening of epoxies, which is a 3-membered ether. That's going to be very important. And then conversion of alcohols to other leaving groups. Like say OH is a bad leaving group. Let's figure out a way to make it a good leaving group. Okay, first thing to talk about is organometallic reagents, okay? There's 2 major organometallic reagents we're going to talk about in this chapter. There's a third one where you can use copper, and that is less reactive than the lithium or the magnesium reagents, so I'm only going to focus on the magnesium and the lithium reagents. When we have a magnesium reagent, we call them Grignard reagents, okay? The guy got the Nobel Prize, he was from France, got the Nobel Prize for this reaction, so it's aptly named for him. And what we do here is we take any halogen bond and we insert magnesium into it with a 2-electron oxidation. We're going to actually take 2 electrons away from the magnesium to generate 2 sigma bonds and create this polar covalent bond, okay? Magnesium is less electronegative than carbon. So carbon's going to hold the negative charge, okay? But it's still a polar bond. It's not a full negative charge. It's only a partial negative charge. But because it has a partial negative charge, it can now act as a nucleophile. So now we have a nucleophilic carbon, okay? And we can do that with benzenes, vinyl groups, or sp3 hybridized halogens. We can also create that same polar bond using lithium instead. And this uses 2 equivalents of lithium. One of the lithiums will give up 1 electron and make that sigma bond with the organic substrate. And then the other lithium is going to give up an electron and react with the alkyl halide, the halide portion here. So we always need 2 equivalents of lithium to generate our alkyl lithium reagent. Now again, it's still a polar bond. It's a polar covalent bond, but lithium is less electronegative than carbon, and therefore it carries the negative charge. So what's very important in these kind of reactions is the use of an ether as the solvent, okay? The most common solvent used in this thing is diethyl ether. Occasionally THF will work, but diethyl ether is required for the reaction to help stabilize that complex between the carbon magnesium and the magnesium halogen, whatever that is. Okay. So the basic reaction is we take our neutral magnesium, take away 2 electrons, create 2 new sigma bonds. Okay. So what does that look like? Okay. So we take 1 electron from our halogen carbon bond and use 1 electron from magnesium to create a new sigma bond. Okay, that's going to generate a free radical on the magnesium itself and a free radical on the carbon itself. They are close enough to each other that they don't have to diffuse away, so they react almost immediately to form a new sigma bond. So in sense, magnesium has given up 2 of its electrons to create 2 sigma bonds, 1 with the halogen and 1 with the carbon. Now, the magnesium halogen bond is now polar enough that it's actually an ionic bond, but the carbon magnesium bond is not polar enough, and it's a polar covalent bond. We have a similar reaction happening in lithium, except we have to give 1 electron from 1 equivalent of your lithium and the 2nd electron from the 2nd equivalent of lithium. That's why you have to have 2 equivalents of lithium. Okay. All right. So the whole point of making these organometallic reagents is to put a partially negative charge on carbon to turn it into a nucleophile. Okay. So let's talk about the character of that bond. Well, I said that there's a difference in electronegativity between the carbon and magnesium. And so that gives it about a 35% ionic character, meaning 35% of the negative charge is on carbon, and and then there's a 35% of the positive charge on magnesium. but that still leaves it as a covalent bond. Now, the lithium itself has a little bit bigger difference in electronegativity, and therefore it's slightly higher in ionic character, and they tend to be slightly more reactive because that higher ionic character. Okay, so as we start to polarize this bond, what we end up doing is leaving both of the electrons in that bond on the carbon, creating a carbanion or a carbon anion, carbanion right here. And as we saw when we talked about carbocations and radicals, carbanions are an unhybridized p orbital that has 2 electrons in it. Okay, so it changes its structure a little bit to generate that anion, but it's not completely dehybridized when it's in its magnesium complex or its lithium complex. Only when it fully ionizes does it turn into this unhybridized p orbital. Excuse me. All right. So now we have something that has a partial negative charge, and we want to react it with things, okay? Let's think about the double bond in an alkene, okay? There are 2 carbons, so that's a non-polar bond with a sigma bond and a pi bond, okay? So it's acting as an electrophile. That pi bond is acting as the nucleophile, right? It's trying to look for positive charges, right? But in the case of the carbonyl, we have a polar bond. And we have that polar bond, we have a partially positive charge on carbon and a partially negative charge on oxygen. This is the key to the next reactions we're going to do, because we have a carbon nucleophile in the Grignard reagent or the organolithium reagent, and we have a nucleophilic target in the carbon of the carbonyl. So it is an electrophile, and it is going to be attacked by nucleophiles. Okay. So what does that mean? Well, that means is we can take a Grignard reagent and attack a carbonyl compound, and in the end, after we add acid, we'll generate an alcohol, because we're going to add to that carbonyl compound, switching the hybridization from sp2 to sp3. And then when it does this, it's going to have a negative charge on oxygen, which is going to be counterbalanced by the magnesium. And then by breaking that magnesium oxygen bond off with acid, we'll protonate the alcohol, generating our organic substrate. So overall, that seems like a pretty simple mechanism, right? Nucleophilic attack, followed by the transition of the magnesium over to the oxygen. And then when we clip it off with acid, it turns into an alcohol. But what kind of alcohols can we make? Well, turns out you can make a lot of different kinds of alcohols. We can make primary, secondary, or tertiary alcohols by choosing the carbonyl compound you're attacking, okay? If we want a primary alcohol, we need to choose a carbon that already has 2 hydrogens on it and some kind of oxygen. Well, we have that if we look at formaldehyde. Formaldehyde is our simplest aldehyde. It has those 2 hydrogen bonds, those 2 hydrogens bonded to the carbonyl, and that's going to give us our primary alcohol when we attack it with a Grignard. So we're going to do an addition reaction onto this sp2 hybridized carbon, giving us our intermediate. And then when we work it up with acid, we end up getting our primary alcohol. Okay, I don't want a primary, I want a secondary. Well, all you have to do is you have to have 1 hydrogen on that carbon to get your secondary alcohol, which means any other aldehyde will give us a secondary alcohol. Okay, so primary alcohol with formaldehyde, secondary alcohol with the aldehyde. Okay, but how do you make a tertiary? Well, that's easy. You have 2 R groups on there already, so you just start with a ketone. When you hit it with a ketone, you can turn it into your salt here, which gives you your tertiary alcohol. So see how useful Grignard reagents are? You can make primary, secondary, or tertiary alcohols. And I'll even do you one more. You can even make carboxylic acids. In the case of the carboxylic acid, we have to attack a different kind of carbonyl compound. In this case, we're attacking carbon dioxide, which is basically like two carbonyls hooked to the same carbon. In the case of carbon dioxide, we're going to do that same addition reaction to the carbonyl carbon. When it does, it's going to kick out one of the double bonds, leaving the other carbon-oxygen double bond untouched. That's going to give us our carboxylic acid salt. And once we acidify, we end up with our carboxylic acid. So the Grignard reagent is allowing us to get primary, secondary, tertiary, and carboxylic acids. And by choosing whether you want it to be symmetrical or not, you have to choose what your different R groups are. So you can choose whether it's fully symmetrical or not symmetrical, or fully symmetrical or not symmetrical. Okay, so the general mechanism is the same for all of these, okay? You have a partially positive carbon in your carbonyl. You have a nucleophile in that partially negative charge on the Grignard reagent. You go ahead, those two electrons come in and add to the carbon, kicking out the electrons from the double bond onto the oxygen, which then is counterbalanced by that magnesium salt. Once we clip that magnesium salt off with acid, we've protonated the alcohol and we've generated our final product. Okay. Ooh. That's not what I wanted. Okay. So, okay, great. We can attack carbonyl compounds with these Grignard reagents. Well, what else can we do with it? Well, you could also look at esters. Esters have a carbonyl in them too, but esters are different, okay? In the case of our attacking an aldehyde or a ketone, if we were looking at what possible leaving group was there so that we could reform the carbonyl, you would have to lose a carbon-carbon bond or a carbon-hydrogen bond, which means the carbon leaving as a negative, you just had one come in, that's not going to happen. Hydrogen leaving as a negative, that's not going to happen, so you get the addition product. However, in the case of Grignards, that first step is the same. You attack the carbonyl. But when you attack the carbonyl, you now have a decent leaving group in the alkoxide. That alkoxide is a weaker base than the base created by the Grignard reagent, and therefore it can leave and regenerate some of the carbonyl. When it does so, it actually makes a ketone intermediate. But now you have a ketone in the presence of a Grignard. So the Grignard reagent is going to attack the ketone and give you a second substitution. And when you add acid, you end up with an alcohol. So when you have organolithium reagents or Grignard reagents attack an ester, you end up with a tertiary alcohol. But two of the R groups are what your Grignard was, always, okay? So you have to have two equivalents of that. It's not selective enough to add one than the other. You have to have two equivalents. So now we're looking at symmetrical versus non-symmetrical. If we're adding two of the same group, you might want to start with an ester, and then you can add both of those equivalents at the same time. Questions on that? So the mechanism is fairly straightforward. Just don't forget, you always have acid at the end to reprotonate to give you your alcohol back. Okay. So, and the general mechanism is, like I said before, we have the ability of the alkoxide to leave as a weaker base than the nucleophile that came in. The alkoxide is still a fairly good base, but the Grignard is a much stronger base, and therefore the alkoxide can leave, regenerating our carbonyl. Any carbonyl will then be attacked by that stronger base, in this case, the Grignard reagent or the organolithium reagent, generating our salt intermediate, which then we decompose with acid to give us our alcohol. All right, questions about Grignard reagents. Okay, we made them really strong nucleophiles. All right. But I said we made them really strong nucleophiles, but when I said they were also a stronger base than alkoxide, well, we can use that to our advantage, because if you wanted to actually put a specific isotope of hydrogen there, you could use that, because the Grignard reagent abstracts a hydrogen from protonated solvents. It can be anything from an amide to an alcohol to a water. If it has a proton that can be abstracted, it will. Okay. So in the case of a Grignard reagent like this phenyl Grignard here, it reacts with water and we end up with a hydrogen where that halogen was. So if you want to remove the halogen and just have your hydrocarbon, this is a good way to do it. You make your Grignard and quench with water. Most of the time we want to use it as a nucleophile, and so we want to find some carbon to attack. But let's say you wanted to probe a reaction mechanism by adding a different isotope of hydrogen. In this case, we're adding deuterium. We can do that too, again, by creating that nucleophilic, creating that negative charge on carbon, and then it will go out and pull any proton off any acidic compound and create a carbon-hydrogen bond, or in this case, a carbon-deuterium bond. Okay, so we've made carbon nucleophiles from alkyl halides, aryl halides, and vinyl halides. Okay, we can also make a carbon nucleophile out of acetylene. Because acetylene is the most acidic of the hydrocarbons, we can use a strong base like Grignard reagent or lithium reagent, or even sodium amide, which is a slightly weaker base. And we can attack it. We can deprotonate the alkyne to generate a carbon nucleophile. Okay. So in the case of the Grignard reagent, it ends up producing a hydrocarbon, which would have a pKa of around 60. In the case of butyllithium, again, we create a hydrocarbon, butane, with a pKa above 60. In the case of sodium amide, we end up with creating ammonia, which has a pKa of 36. So all of those are very weak acids, and therefore all can be used to deprotonate acetylene. Okay, so now that we have another kind of carbon nucleophile, it's going to be the same mechanism. The nucleophile is going to attack the carbonyl carbon. It's going to create some kind of salt that then has to be worked up with acid to generate our final product. Okay, so this is really good if you want to add your one carbon or your alcohol to the end and have an alkyne in the middle of your chain somewhere. So if you look at a product where you have an alkyne next to an alcohol, it was probably made by attacking a ketone or aldehyde with the acetylide ion. Excuse me. Green tea's just not working today. Okay. All right. So that's the first reaction we have to make alcohols. We add across a carbonyl. Okay. Let's find another way to make alcohols. Okay. Let's do it by reduction. Okay. But before we talk about reduction, we got to talk about oxidation states again. Okay. So our lowest oxidation state possible is having 4 hydrogens on it, and each hydrogen gets a -1. So 4 hydrogens has methane at a carbon oxidative state of -4. The highest oxidized is CO2, which is 4 bonds to oxygen. So that's 4 plus 1s, 4. So everything else in the middle is a single electron difference between the different systems. So in the case here, or a single oxygen bond difference between them. So in this case here, we have 0 oxygen bonds, 1 oxygen bond, 2 oxygen bonds, 3 oxygen bonds, and in CO2 we'd have 4. Okay, so think about it as the losing of a hydrogen or the gaining of an oxygen bond. So in the case of reduction, we're going to reduce the number of bonds to oxygen. So if we want to make alcohols, that means we're going to have to reduce a carbonyl compound to break one of those double bonds and create adding 2 hydrogens across that, what used to be the carbon-oxygen double bond. And we have 2 reagents to do this, and we call them hydride transfer reagents. Okay. The first one is called lithium aluminum hydride, because it has lithium, aluminum, and 4 hydrogens that carry each a negative charge. And we have sodium borohydride. So we have sodium plus boron and 4 hydrogens that can transfer with having hydrides, which is a hydrogen with a negative charge. Now, there's different selectivities between these. Sodium borohydride is less reactive than lithium aluminum hydride. Therefore, it's more specific about the types of carbonyl compounds that it will reduce. Okay. Now, sodium borohydride is actually typically used in with a little bit of water or alcohol and does not burst into flames. However, so lithium aluminum hydride does react very violently with water, puts off lots of hydrogen, and has a nice little poof, little yellow-white flame coming out of it. I've done it, it's not fun. Anyway. So what can we do? Well, let's talk about the sodium borohydride first, lithium aluminum hydride first. So what we're gonna do is we're gonna transfer 2 hydrogens when we're gonna add those to the carbonyl. So we're gonna put 1 hydrogen on the carbon and 1 hydrogen on the oxygen, and that's gonna turn it into an alcohol. So in the case of a ketone, we're gonna go from an oxidation state of +2 because it has 2 bonds to oxygen, and carbon doesn't count, it's 0. And we're gonna add 2 hydrogens to it, breaking it so we have 1 less bond to oxygen and we have 1 more bond to hydrogen, changing our oxidation state to a 0. Okay. So our lithium aluminum hydride is adding across that double bond hydrogen on each side of that carbonyl. In the case of an aldehyde, we can actually also get an alcohol, but in the case of an aldehyde, we get a primary alcohol. Remember, if we take primary alcohol and we oxidized it, we got an aldehyde. If we use the special reagent, oh, never mind, sorry, we haven't done that yet. All right, the other thing we can do is lithium aluminum hydride is actually very reactive and can react with carboxylic acids and esters. In the case of an ester, it'll actually add across the carbonyl and it'll take away that the alkoxide bond. And so we'll end up generating a primary alcohol. Okay? In the case of the carboxylic acid, it's going to lose water as one of the hydrides transfers, and it's going to add across that double bond, and we end up getting a primary alcohol. So in the case of lithium aluminum hydride, the ketone is the only one that's going to give us a secondary alcohol. Aldehydes, esters, and carboxylic acids will give us primary alcohols. In contrast, sodium borohydride is not as reactive. It will not work with the esters of the carboxylic acids. It cannot reduce that carbon-oxygen single bond. And because it cannot reduce, it's not going to react at all. But it still likes the carbonyl, and it will add across the carbonyl, generating primary or secondary alcohols. So here's where you have to be really cognitive of what your substrate is and what your product is. Because if I say reduce down this ester to a primary alcohol, you will not be able to use sodium borohydride. You must use lithium aluminum hydride. Questions on the selectivity of these 2 hydride transfer agents? Don't worry, I'm going to do the mechanism next. Okay, so I'm not doing the, oh, there it is, good. Okay, I just want to make sure I was doing the mechanism next. Okay. The other thing about these reducing agents is because we're transferring a hydrogen with a negative charge on there, they are selective about only attacking carbonyl compounds, okay? So in the case of, if you have a double bond in a system that you don't want reduced, then you need to be careful about how you do it. If you had a double bond and a carbonyl and you try to use catalytic hydrogenation with platinum, palladium, or nickel, you'll actually reduce down the carbonyl compound to the alcohol, but it'll also reduce down the double bond. Remember, we use that catalytic hydrogenation to reduce down double bonds. Okay. However, if you use one equivalent of hydrogen, you can, because the alkene is more reactive than the carbonyl, it will go first, but it's very hard to regulate that. So we rarely use catalytic hydrogenation to reduce down carbonyl compounds selectively. Okay. But because the sodium borohydride and lithium aluminum hydride are very selective to carbonyls, they do not react with double bonds. The double bond's not polar. It's taking advantage of the polar nature of the carbonyl to add across that partially positive carbon, partially negative oxygen, to give us our final aldehyde, our final alcohol from our aldehyde or ketone. So we can selectively reduce down just the carbonyl in the presence of the alkene. Okay, so why can we selectively reduce down the carbonyl in the presence of the alkene? Well, it's all about the mechanism of the system. So the first thing we're going to see here is that a hydride is a hydrogen with a negative charge. Okay, so your hydrogen with your negative charge is your nucleophile. And it will selectively attack a carbonyl carbon because of its sparsely positive charge. When it does this, it's going to go ahead and open up the double bond, giving the negative charge on the oxygen. The oxygen is then going to react with something in solution to protonate it, and you'll end up with your alcohol and some of the alkoxide that was from the solvent. Now notice that it depends on which alcohol is more basic or which alcohol is more acidic to see which where it's going to be in equilibrium as to who has the proton. So at the end of the reaction, when you hit it with water, they'll all be protonated. So now you've transferred one of those hydrogens from the boron. Now it's boron with 3 hydrogens and it's neutral. Okay, how do we go forward? Okay, well, we actually use that alkoxide to attack the boron and create an intermediate boron salt here. And notice there's a negative charge on boron again. When there's that negative charge on boron again, that means one of those hydrogens can attack as a nucleophile on the carbonyl, and that will perpetuate until all 4 hydrogens are transferred. So you can use 1 equivalent of sodium borohydride for 4 equivalents of a carbonyl compound because the reaction will perpetuate itself in alcohol. Questions about the mechanism? The key here is about that name, hydride transfer agent. Hydride is a hydrogen with 2 electrons and a negative charge. Okay, so with lithium aluminum hydride, it's similar in nature. In fact, we still have a hydride transfer. We have the one of the hydrogens on the aluminum act as a nucleophile, and then it generates an aluminum alkoxide salt. Remember, lithium aluminum hydride is done in the absence of an alcohol, in the absence of water, because it'll react with it and heat up. So it keeps the alcohol generated by the addition of hydrogen on the carbonyl as its counterbalancing ion. But it still has 3 more hydrogens to transfer. So it's going to transfer another one of its hydrogens, and it's going to make a dialuminum salt. But it still has 2 hydrogens to transfer, and it'll keep doing that until the end of the reaction, when all 4 hydrogens are transferred and the aluminum has 4 oxygens around it. Now we have to work it up with acid to break that aluminum oxygen bond, and we're generating our alcohol, lithium hydroxide, and aluminum hydroxide. So the overall reaction looks like 4 equivalents of your carbonyl compound to 1 equivalent of lithium aluminum hydride. And then with the water workup, we generate our primary or secondary alcohol. Okay. So again, here, the mechanism is all about that negative hydrogen transferring to the carbonyl. All right, so with the ester, it's a little bit different, because with the ester, what we're going to end up doing is generating an alkoxide. We saw that in before that the aluminum wanted to have an alcohol salt to counterbalance it. And so what happens is we have the regeneration of the carbonyl by kicking out an alkoxide salt, which then can react with the lithium aluminum hydride. Now we have addition by another equivalent of the hydride transfer agent to get back to this now tertiary alkoxide. And then when we protonate at the end, we have our tertiary alcohol. So in that presence of your aldehyde or ketone, you're going to get a primary or secondary alcohol. in the presence of your ester. Oh, this is the wrong mechanism. That's the general mechanism for the attack on there, showing you the alkoxide kicks out. In the case of this, we're going to end up with a primary alcohol. We got that primary alcohol from the aldehyde. We got a secondary alcohol from our ketone. With our esters, we're going to end up with a primary alcohol. And so the first step, again, is the formation of our new hydrogen bond here. But then it's going to kick out the alkoxide again, regenerating our carbonyl. Then that's going to react with another equivalent of lithium hydride, transfer another hydrogen to give us our alkoxide salt. After we work that up, we're going to end up with our primary alcohol, our alcohol that was part of our ester, and then our salts again. The mechanism is pretty similar for the carboxylic acid, except instead of eliminating alkoxide, what we're going to end up doing is we're actually going to have the lithium eliminated with the the oxygen transfer to the aluminum first. In the previous mechanism, we made that salt, right, with the aluminum oxygen here, and then the oxygen stayed attached to the carbon. That doesn't happen in the carboxylic acid. In the carboxylic acid, the oxygen that was the acid is transferred to the aluminum and regenerates our carbonyl compound, in this case an aldehyde, and an aluminum oxide with 2 transferable hydrides. We put another equivalent of the lithium aluminum hydride in here, and of course it adds across the double bond, generating our alkoxide salt, and upon acidification we end up with our primary alcohol. So the difference in mechanism here is we actually are transferring the oxygen to the aluminum. In the ester reaction, we're actually liberating an equivalent of alkoxide. Questions on that? Okay, so by choosing the correct reagent and choosing the correct substrate, we can get primary, secondary alcohols from aldehydes and ketones by reduction with either reagent, and we can get primary alcohols of esters and carboxylic acids if we use lithium aluminum hydride. All right, so now let's go from an alcohol to something else. Okay, so this is a reaction of an alcohol. So when we think about oxidation, we think about going to a higher number of bonds between carbon and oxygen. And so what we're going to do is we're actually going to use an oxidizing agent called chromic acid. So imagine it's CrO3 that we add water to. And that turns into chromic acid here. So in the presence of water, chromic acid can be protonated. And then the alcohol, the lone pair on the alcohol, acts as a nucleophile and adds to the chromium center, generating a salt. Okay. Now, if we remove this hydrogen and transfer it to one of the OHs up here, it can leave as water. And when we do that, we generate a chromate ester. Okay. So in this generation of this chromate ester, that's our intermediate here. But now water can come back in, or in this case, acid can come back in and attack, protonate one of the carbonyls of the chromate ester on the chromium, and that will eliminate one of the waters is going to act as a base and eliminate one of those hydrogens that's on the carbon oxygen bond. And when you do that, you generate a carbonyl. Okay. So we are going from our alcohol, we are creating our elongated chromium oxygen carbon bond, and then we're using water as a base to eliminate one of the hydrogens to generate a carbonyl compound. Okay, now notice we generate an aldehyde here, but that aldehyde can also be oxidized because it already has a hydrogen still here. Okay. So in the case of having an aldehyde in the presence of water, it actually adds water across that double bond and we end up getting what we call a hydrate or a geminal diol. That geminal diol is reactive toward chromic acid and will react with it, and then will oxidize, take off one more hydrogen, this remaining hydrogen, and gives us a carboxylic acid. So primary alcohols using chromic acid reduce down to carboxylic acids. However, if we don't have that hydrogen of the aldehyde, we have another R group there, it actually stops at the ketone. Okay, so in the case of our primary alcohols, we produce a carboxylic acid. Secondary alcohols, we produce ketones. Well, what about tertiary alcohols? You don't have a hydrogen on that carbon where the oxygen is, so they don't react. You cannot oxidize readily a tertiary alcohol. We'll just form the chromate ester. There's no hydrogen for the water to eliminate. And if there's no hydrogen for that water to eliminate, then there's no forming of a carbonyl, and the reaction is not oxidized. It's like, okay, well, if we had a primary alcohol, we did form an aldehyde there in the middle, can't we just stop it there? Well, not with chromic acid. That presence of water in the system makes it impossible for it to stop at the aldehyde. We have to use a different reagent that does not have water in it. If it does not have water, it can't form the hydrate, and it can't continue to oxidize. So what would that look like? Well, chromic acid, is going to dissolve in water. It's not going to dissolve in almost any other solvent. So we need to trick it to dissolve in organic solvent. So what we do is we're going to make a complex out of it. And the way we do that is we take pyridine, which is this good solvent here, and HCl, and we're going to make a compound called pyridinium, which is the protonated pyridine, chlorochromate. The great thing about pyridinium chlorochromate is it now is dissolvable in polar solvents like dichloromethane. Okay, so in this case here, we're using this as a sort of polar solvent, but it's a solvent without water in it. Okay, if there's no water in the system, it can't hydrate, and therefore we stop at the aldehyde. So we can take our primary alcohol using PCC, or pyridinium chlorochromate. We can then stop at the aldehyde and isolate that product. Again, this is very selective. It's the only way to oxidize a primary alcohol to an aldehyde. Okay, so you can use chromic acid on any primary or secondary alcohol, and you'll get either a carboxylic acid or a ketone. Or if you want to stop the aldehyde, go with the PCC or pyridinium chlorochromate. All right, questions on oxidation. Wow, we've done a lot of things. We've added across the carbonyl using nucleophiles. We've reduced the carbonyl using hydride transfer reagents. Now we've oxidized alcohols to carbonyls, either carboxylic acids or ketones or aldehydes. What else can we do with these things? Well, we can make alcohols by opening rings. Okay, so in this case here, we have a special ring we're going to talk about. We have a 3-membered ring. It's got a lot of ring strain. It's an oxygen with 2 carbons in it. We call these oxirings, or more commonly, they're known as epoxies, okay, or an epoxide, okay. Because of ring strain, this is going to open up to SN2 substitution, okay. Now, no other, any other ether that does not have ring strain, it will not react with an SN2 reaction. It's only because of ring strain. Okay. So, and it's all about the energy. Okay. So if we look at the energy of a regular ether that does not have ring strain, to get to this transition state where it's trying to break that bond and make that bond at the same time, SN2, that is a very high activation energy. And the product here actually creates an alkoxide and a new bond with our nucleophile. Okay, that's higher in energy than where we started with. So that reaction doesn't happen. However, because of ring strain, we're starting at a higher potential energy. And because that transition state's about the same energy as it was for the other one, we have actually a smaller jump to get to that activation energy. And more importantly, because our product does not have ring strain, it actually is in lower energy and is an exothermic reaction. Okay, so the epoxy is the only ether that reacts with this ring opening attack of a nucleophile. It's like, okay, well, you've convinced me. Nucleophiles will open rings. So what? Well, when you do that, you end up with a nucleophile on one of your carbons and an alcohol on the other. There's a lot of different ways we can use that to our advantage. Okay, for example, if you just attack it with hydroxide as a nucleophile, boom, you have a diol. Not only that, you have an alcohol on the 1 carbon and on the 2 carbon. 1 carbon, 1 carbon and 2 carbon there. So, all right. Now, okay, you don't want to attack with alkoxides. You can attack with other nucleophiles. With hydroxide. Alkoxide is going to give you a ring-opened ether. Okay, still an ether, but it's not in a ring, and therefore it actually is lower in energy. And well, we still have an alcohol as a functional group. Sulfur gives you a thioether and an alcohol as a functional group. A Grignard reagent, that's a good nucleophile. We just learned about those. Gives you an extension, a carbon-carbon bond, and an alcohol on your ring. Lithium aluminum hydride will also add hydrogen across both of those bonds, giving us an alcohol and a hydrogen. Here, the hydrogen is the nucleophile. Cyano gives us cyanoalcohol right here. Now, technically, this is now the number 1 carbon because it's a nitrile, and this is the number 2 carbon. But notice the alcohol remains at the end of the chain. There must be mold in my office, sorry. Okay, so any nucleophile will generate a highly functionalized species from these ring openings of these oxiranes or epoxies. But is it regiospecific? And the answer is yes and no, depending on your conditions. Okay, under basic conditions, under conditions that are not protonated, have no acid in them, what's going to happen is you're going to have attack of your nucleophile on your less substituted carbon because of sterics. Okay, so under basic conditions, under conditions that do not have acid, neutral or do not have acid, you're going to get the more substituted alcohol. Okay, however, if you're doing it under acidic conditions, the first thing that's going to happen is it's going to protonate that epoxy. When it protonates that epoxy, it's going to elongate the bond and it's going to try to form the most stable, partially positive carbon it can. Okay, when you're stabilizing the most stable, partially positive carbon you can, think carbocation stability, meaning you're going to have that more positive center on your more substituted carbon. And that means you're going to open in the opposite direction. Your nucleophile is going to attack your more substituted carbon, giving your alcohol on your less substituted carbon. So looking at the conditions is important to know the regioselectivity of your system. Okay. And the basic conditions work best with strong nucleophiles. The acidic conditions work best with weak nucleophiles. All right, questions on that? Okay. Okay, so what can we do with this? Okay, so in the case of just an epoxy by itself, if we have it protonated here, we have 2 partially positive groups, and then we have water coming in as our weak nucleophile. In the case of our weak nucleophile, we're leaving as, our leaving group is this protonated oxygen or this neutral species. So when we get an attack of that, we end up with our leaving group being our neutral species. And our water now is the protonated species. Now we just have to have water come in and deprotonate that protonated alcohol to yield our neutral species, and we've regenerated our acid. So these are acid catalyzed reactions. But again, we need a weak nucleophile like water or alcohol or bromine or iodine to be to in an aqueous system. They're because of their protonated, they're weaker nucleophiles. We can do this with an acid catalyzed system. Okay. So it'll work with all of these in that acid catalyzed system to generate our alcohol on our least substituted side. Okay. All right. So it's kind of like the mechanism where we had the oxymercurization, demercurization, where it kind of gave kind of on one side, but it gave a partially positive elongated bond. When we had our bromonium ion, when it was unsymmetrical, we had that partially positive side because it would have the more stable side. We get that same kind of regioselectivity and stereospecificity in the acid catalyzed ring opening of oxiranes. Okay? And again, the driving force is trying to form that almost tertiary carbocation before the weak nucleophile comes in to attack. Notice that also gives us some specificity as where the attack is going to happen. Our weak nucleophile is going to come toward the tertiary center, but it's also going to be coming anti to the part that's on top. All right, so does that make sense? Does that regiospecificity make sense on these oxiranes? Again, nucleophile, good nucleophile, least substituted because sterics, poor nucleophile acid catalyzed, creates that strained, elongated bond and gives us our least substituted alcohol. Okay. So in this case here, we can do something where we have this chiral center right here. And when we protonate it, we elongate that bond. And now we also have the attack by our nucleophile is going to be underneath. In this case, we're using a weak nucleophile of methanol. And therefore, we have stereoselectivity and regioselectivity. Regioselective because it goes to that particular carbon. Stereoselectivity because the oxirane is blocking the top of the reaction. And therefore, we can actually get our stereoselective product from our system because we know the nucleophile had to come in from the bottom side and give anti-addition. All right. Questions on regioselective and stereoselective ring opening of epoxies? And again, it's stereoselective on the non-acid catalyzed as well because the nucleophile has to come in from the bottom. It's just going to give you the more substituted, which rarely gives you a chiral center. All right, let's see. We've got a lot more to do. Let's see, we've got a little bit of time, so we're gonna, okay. So when we're thinking about these ring openings of oxiranes, think that if you have a good nucleophile, it wants to come in and react very quickly, and therefore it's going to have sterics be the #1 demand. And so a good nucleophile is going to always go for the less substituted carbon. If you have a poor nucleophile, it can wait around till that partially positive charge is generated. And it will wait around until that partially positive charge is generated, just like the poor nucleophiles waited around for the full carbocation in our other mechanisms. That gives you regioselectivity for the good nucleophile versus the acid catalyzed bad nucleophile. Stereospecificity comes from the fact that your oxirane is already in a position where your addition has to be anti, depending on which carbon it goes to give us when our ring is open. All right. Okay. And this can be very obvious when we do these in rings. Remember, we like to do things on rings because it doesn't have the free rotation and it's easy to see where the things happen. Okay. So in the case here, we have enantiomers. We have our mirror image of our two compounds here that are non-superimposable. So this is our RS, and this is our SR for our system here. Okay. Now, in the case of an acid catalyzed system, okay, we are going to have the generation of the more stable positive charge on the more substituted carbon. Okay. So when we get that to happen, we have to have, again, the bromine come in from the backside of the bond that is being broken. It's still an SN2 reaction. It has to come in from the backside of the bond that's being broken. So that gives us our bromine on this bottom side, which actually flips our methyl group to the top in this condition. So we have to have that anti-addition because it's an SN2 reaction. Now, if we had the other isomer, we would again tack bromine at the other side, again, at the more substituted side, but in the anti-addition as well, generating a different isomer. So in this case, we get the SS. In this case, we get the RR. Okay. Do you see how it's regioselective and stereoselective in both cases? It attacks the same carbon and it attacks anti to the oxygen, which is the leaving group. The protonated oxygen is the leaving group. SN2 reaction. All right. So that's a weird jump. Oxidation of alcohols to aldehyde to ketones and carboxylic acids. We can use a different reagent for that. If we have a primary alcohol, we saw that by using chromic acid, we would get the aldehyde, but then it would immediately oxidize to the carboxylic acid. And so we could go from our primary alcohol to our carboxylic acid. And by using a special reagent in the absence of water, we could stop at the aldehyde. In the case of our alcohol here, we also are going to introduce two new oxidizing agents here. This is potassium perchromate, and this is permanganate here. Notice both of the first two here. In fact, I'm going to erase this one. I want to draw something else around it. This one right here is under basic conditions. The other two are under acidic conditions. Okay. So sometimes it'll be our advantage to use something in the acidic conditions or something in the basic conditions. So in both cases of the permanganate or any of these chromate oxidizers that aren't PCC, they'll oxidize your primary down to carboxylic acids. They'll oxidize your secondaries down to ketones, and your tertiaries just don't react because there's no hydrogen to take away. Now, yeah, so this is the first time we've introduced the potassium permanganate for the oxidation of alcohols. We did use it in the addition across double bonds. Most of the times it actually broke the double bond, but we can use this as an oxidizer to take alcohols to aldehyde, to ketones and carboxylic acids. All right, that slide's in the wrong place. I'm sorry about that. That should have been in the previous section. All right, questions on that? Okay. All right. Okay, we'll start. Let's see, how many slides do I have on this? Okay. I kind of want to stop there because the rest of it, I want to make sure we get all turning oxygen into a better leaving group and the ethers all together. So I'm going to go ahead and stop recording and post this. And if you want to stay back and ask questions, please do. If you got to run off, please do.